Log on, tune in, find out. Another good idea from Cambridge.
This is Professor Luc Robbiano from the Université de Versailles, and he will give a talk on Carleman estimates of Zaremba boundary conditions.
Thank you. I would thank the organizer for the invitation, and I speak about a joint work with Pierre Cornillo. So we consider a wave equation on a domain of Rn, and in this talk all the function of all the domain, all the manifold are smooth. So except the solution, they are not smooth in general. So, and the wave equation, we consider boundary condition. We split the boundary in two parts, and on this part, we take the Dirichlet boundary condition, and the other part, we consider the Neumann condition with a damping term A. A is positive, A is not identically 0, and for this kind of problem, the energy decay and goes to 0 when t goes to infinity. And the problem is to obtain estimate on the energy. We have in this context we have two results. Of course, there are a lot of results, but we consider only the result where we not suppose here that any geometrical condition on A. So in this context, we have the two results. The first is we consider the wave equation with a damping in the interior. So the picture is the following. In this case, we have omega, capital omega, and we have the support of A in on the small part of omega. And the second problem is the same, the wave equation with a Neumann boundary condition with a damping term on the boundary. In this case, we have the same picture, but the support of A is on small part of the boundary. And in the two cases, we have this estimate. The energy is estimated by a logarithm term like this. And this is for smooth solution. Smooth means that U is in a domain of the generator of the semi-group associated to this problem. So I don't describe more this. For Zaremba boundary condition, we have the same result. So I don't give a precise theorem, but it is the same as before. And actually, we don't study the problem for wave equation because this estimate is related with a stationary problem. So formally, we replace the derivative with respect t by I lambda, and you obtain this problem. And the link between the two problems is given by a theorem of Burke, and he tells us that if V in energy norm is estimated by F0 and F1 with an exponential term, then we have the estimate of the energy. So in the sequel, we study this problem. So in my talk, in the first part, I will try to explain how we can obtain this kind of estimate. To obtain this kind of estimate, we use an interpolation estimate. So in the second part, I give some idea to obtain the interpolation estimate using Carleman estimate. And in the third part, I give some idea to obtain Carleman estimate for the strange Zaremba condition. So we need two estimates to obtain the estimate on the resolvent. So the first tool is we multiply the first line of the equation by V bar, the conjugate of V. We obtain this equality, and we integrate by part to obtain these two terms, and we obtain some term on the boundary. And we replace this normal derivative of V by these two terms, and you have obtained this. And we take the imaginary part of this equation. So these two terms disappear, and you can estimate this by the data F0, F1. And A is positive, V bar is positive, so you assume lambda larger than 1, and you have an estimate of V on the part of A is bigger than delta, it's a parameter, by the data with this term, but it's not important. We see that in the sequence. So now we introduce interpolation inequality. So I take the equation, the system with the boundary condition, and we replace lambda by you introduce an additional variable x0. I denote x0 x in actually, but it's not a problem. So, and we replace the power of lambda by the derivative with respect to x0. So it's easy to find this equation on W. It's not essential, but it's convenient to have this system. So maybe I give some picture for y, x, and don't know. So we have the variable x0, and omega is this, and you choose some parameter 0, 1, 2, and denote this set y and this set x. And we have a part of boundary small gamma. And we assume that we have this kind of interpolation estimate. So these three terms are the data in some sense. And you can estimate W in a small part by the data and W in a larger domain. This two facts. If lambda is 1, so this term disappears. This estimate is false. So it's important. False because it is well known that when you have an estimate linear, the operator must be hyperbolic. It is not possible to have a linear estimate for elliptic equation. And another fact, not for important, but if
n
gamma, small gamma, yeah.
Yes, is d omega n or d omega? Because d omega d
omega.
is 0, so it's if you take gamma there.
Yes, I forget. Gamma is chosen later.
Okay.
Gamma is chosen later. So its nu is 0. It's trivial. It's important, in fact, but so I return in the second part of my talk on this. So I can now finish the proof. We have this relation between V and W, and we can estimate W on X by V with the exponential term. I take lambda positive too. And I can estimate V by W with this exponential term. And we can estimate the trace of the normal derivative of W by the data and V. V it's here. So you can estimate W by dx0 of W is related with V on the part. So with the interpolation estimate mentioned above, we obtain this kind of estimate on V. We can estimate each term in this inequality by a term of V. So we want the same estimate without this term to obtain an estimate on the resultant. So now we use the previous estimate. So this is the estimate obtained before, and this is the estimate obtained because we have a term A. I proved this before. So I can estimate now, I take a very small part of this term and a very large part of this term to estimate. I take 10, but it's not real important. And this term now can be estimated by this one. And sorry, it's not the it's not the case. Sorry, this term can be estimated by this one if I take gamma, the part of A where A is larger than delta. So I choose gamma now, and I estimate this term by this one, and this one is estimated by this one, and this exponential multiplied with this term, we can absorb this term, the right term by the left term. It's the same term. So at the end, you obtain the estimate on the resultant. So the main tool is this estimate obtained by the interpolation estimate. So I recall the Carleman estimate. So we need 3 Carleman estimate. The first is a Carleman estimate in interior. So I consider a neighborhood D, and D is without this part of the domain, and I take U supported in D. So in this estimate I have no boundary condition, and the level set of phi is this, and we have in this case the Carleman estimate. The power here is important to prove the Carleman estimate, but not to prove the interpolation estimate. You can forget this power. So this is the first Carleman estimate we need. The second Carleman estimate is with a boundary. So it's the same in the same case, but U now is supported in D plus, and have some trace. The traces are not 0 in this, but I consider only the trace on this line. The trace here are null. So I have the same Carleman estimate. At the left, we have an estimate on U on D plus, so in the half plane. And at the left, we have the same term as before, and I have two terms, the trace of U and the trace of derivative of U. And we have a second Carleman estimate at the boundary. It's this one. We have U is supported in D minus. D minus is the domain without this part. And in this case, we obtain an estimate of on U. You have the two terms at the interior, and we estimate the two trace of U, two trace on this part, always on this part, by the Laplacian of U and the boundary condition. This estimate depends on the boundary condition. For instance, we can prove this estimate for if you have a Dirichlet boundary condition or Neumann boundary condition. In the third part, I try to prove this estimate for the Zaremba boundary condition. Oh, yes. So, now I try to explain how we can find an interpolation estimate if we have a Carleman estimate. So, the data is V. V is not supported, the support of V has not a property. So, we cannot apply directly the Carleman estimate because Carleman estimate, we assume that you have U is supported somewhere. So, to apply Carleman estimate, you cut off V and you denote by U the function chi V. Chi is have the following form: is 0 in the disk, is 0 in the exterior, and is 1 between these two lines. We can. This line is red, but I don't know if you see that. So, and in this part, but chi is between 0 and 1. And now we can apply the Carleman estimate to U, and you compute the term. So you have the first term is Laplacian on V. On of course this is between these two lines. So the important fact is phi is less than C phi. And you have two terms, error term if you want, living between these two lines, C5 and C4, and in these two lines. So I put these two terms here and here. C5 is larger than C4, that's larger than C3, and etc. And
The last estimate is 5 less than C2 and more than C1?
yes, but it's not important. It's not important because the formula is too long in the slide. So maybe the important part is here we have C5 and here C2. And at the left, you keep only the part of U, the part of this estimate, between these two lines, between C3 and C4. So we have this estimate on V. So I repeat the estimate, the previous estimate, and now I estimate the weight on each domain. At the left, the phi is bigger than C3, so I can estimate this term by exponential C3 over h. In other part, other side of the inequality, I estimate 5 by C4, C5, and the same thing là for this term. This gives these two terms. And for this term, I estimate, but 5 here is less than C2. It's easy. And I put this term at the right, and I obtain with other constant. C5 is bigger than C3, so I have a positive constant here, but C3 is larger than C2, so I obtain a negative constant here. So I repeat the previous inequality. And now I choose H. I choose H such that the two terms are equal. It's the simplest way. So I put this H in this equation, and I obtain the interpolation equation. Of course, here it's a local interpolation equation. So two facts that the Carleman estimate is are proven when H is small. So it is why H is small in this choice. So yeah, there are two possibilities. If H is small, it's okay. We can you can do that I say. And if if the choice here H is large, actually this means that this term is very, very larger than this one. So actually this inequality is trivial if you have this estimate. So you have two possibilities. Either you find H, it is good, or either you cannot find H, and it is good also. So the strategy to prove the global interpolation estimate is the following. You have your domain. In this part of the domain, A is larger than delta. If your small gamma in previous slide, and at the beginning you obtain an estimate in a neighborhood of this part by the second Carleman estimate. You apply the same tool here to obtain an interpolation estimate in a neighborhood of this part. After, if you consider a small part here, and you can propagate the interpolation estimate by this local interpolation estimate in the domain omega, except in a neighborhood of the boundary. And now we apply the third Carleman estimate to obtain an interpolation estimate up the boundary in this part. In this part, it is a Carleman estimate proven with Gilles Lebeau, and in this part. So maybe I go with some chalk. You obtain by all the Carleman estimate an interpolation estimate, in this part. And we must obtain now a Carleman estimate in the neighborhood of this manifold where the boundary condition change. So it is the only work is in this neighborhood. So I skip this. the result obtained with Pierre is the following. We have the Carleman estimate with a classic term in the interior. At the left, we have Laplacian. At the right, the boundary, the Zaremba boundary condition. And we obtain an estimate on the trace. In some space, it is not exactly the same space as before, but maybe for this talk, it is not essential. So, this is the Carleman estimate obtained with Pierre. So, I give some idea of proof now. So, I change a little bit my picture. So, first I assume that all the space, the variable as I show the coordinates such that xn is a domain, xn positive is a domain. x1 I show the Neumann boundary condition if x1 is positive, and in x1 negative we have the Dirichlet boundary condition. And I take the Laplacian and I compute like Jérôme yesterday the conjugate of the Laplacian with weight, and we obtain the operator P phi, and the operator P phi has the following symbol in semi-classical sense. Q2 and Q1 are this term. The important fact for the boundary condition is the root. The root of the symbol, the root with respect xn. And we can describe the root, and we have an important quantity given by mu. It is easy to see, for instance, that if you have a real root of this polynomial, you must have the real part 0 and the imaginary part 0. You have these two equations. It is easy to find xn by this equation, and if you put xn here, you obtain this quantity. So, if this quantity is null, you have a real root of this equation. But the mu give also other information. If the mu is bigger than this quantity, actually you have two roots. The roots are simple, and one is bigger than minus phi prime xn, and the other, the imaginary part of the other, is less than the same quantity. So the picture is the following. I draw the complex plane. You have the minus I of phi prime, and so you have if xi prime is large, you have two roots like this. When xi prime is smaller, you have this root become real, and after this root stay here, and maybe this root can cross this line, and maybe the two roots can be double. So you have only one root in this case. So to prove the estimate, we distinguish two cases. When mu is bigger than min phi prime xn, in this case the roots are simple and we have this estimate, and the case of mu is negative. In this case, when mu is negative, the two roots are in the lower half plane. And I choose here phi prime xn sorry, they are not minus. Yes, see, yes. They are minus. So I choose phi prime positive. Oh, the first case, mu negative, is more easier. The two roots are have a negative imaginary part, and we start with an equation p phi v equal f, and we extend v in xn negative by 0, and I denote this extension by underline v, and we compute p phi, and we have a jump here, so we obtain two Dirac mass on xn equals 0. Gamma 0, gamma 1 depends linearly on v and normal derivative on v. So with this equation now is defined in Rn. So we can you can use pseudo-differential calculus. You choose on parametrics on p phi actually, and you can forget R. Essentially, we have QP equal identity, and you apply to in the both sides of the equation, and you obtain a formula. C0 and C1 depends of these two terms, and you restrict this equation on xn equals 0. Actually, we take the limit when xn goes to 0 by a positive value. So we obtain this kind of equation. Now, to understand this equation, I must say what is C0 and C prime naught and C prime 1. So these two operators are Calderon operator, and they have the following form. Xn mu is the Fourier transform of the Dirac mass. 1 over p phi is the parametrics of p, and this is the Fourier transform of gamma 0 of gamma 1. So the C0 and C1 have the following form, and this integral here do not depend of gamma, so you can compute this. You can compute by the well-known residue formula, and as the imaginary part of rho j is negative, this integral is null. It's a well-known exercise in a holomorphic course. So these two terms disappear, and we have this kind of formula. Of course, you have an error term here, but it's not important. So you can compute V, the trace of V, by the data F. And for the normal derivative of V, you can play the same game, and you have the same, you have an estimate. So in this region, micro-locally, you have an estimate of the two traces without trace condition, without a boundary condition. Of course, we need a boundary condition for in the other case. In the case where mu is bigger than minus phi prime xn squared, you can factorize the polynomial, and you can, modulo some error term, factorize the operator p phi. It is I don't write the error term is not important. So maybe it is clear that to an operator C I associate to a symbol C I associate the operator H over I D. And I denote this part by Z. So, and now I extend Z by 0 at the left, and I compute this operator on underline Z. And I find the second F, and the jump of Z on xn equals 0. And now it's the same game. The imaginary part of the root is in lower plane, in complex domain. So you can find the trace of F by the second member of the equality F. So you obtain Z by something related to F G. And then xn equals 0, Z is here. So you obtain the trace of the normal derivative and the trace, this operator on the trace of V. So I repeat the same equation. Now I need the boundary condition. So the boundary conditions are on U and not on V. So maybe I skip this. You can obtain the boundary condition on V. And I change the variable, the unknown variable. I prefer to consider V0 the trace of V, but V1 is a mix between the two trace conditions. And we have V0 null on x1 negative and V1 null on x1 positive. And this equation is written in V1 and V0. So I repeat the equation here. So the naive idea is to restrict this equation on x1 positive and this term disappear. The problem is that we cannot compute this operator because this operator does not satisfy the transmission condition. I'm sorry, it's the same name, it's the same name, but it's not the same thing that the transmission for elliptic problems. So it is also thing. So we cannot take the restriction of x1 positive. So it's well known. There are a lot of work on pseudo-differential boundary problems studied by Eskin, Bouten-Monvel, and so on. But it is not so easy to understand this theory. So before taking the restriction, we must change a little bit this operator. So we introduce this operator, and this operator is holomorphic if imaginary part of Xi1 is positive. So the kernel is supported when x1 is negative. So and you change the variable the unknown v0 and v1 in z0 and z1, and z0 is supported in x1 and z1 in x1 positive and x1 negative, and you change this equation by this one. Maybe it's time. So, and now you can restrict this equation and you can compute this. So maybe it's enough.
Are there any questions? Oh, if it's not the case, then thank you again, and it's